Right. But what if you could predict it? What if you knew who was going to walk out the door before they even reached for the doorknob? That is our mission today. We aren't just talking about the theory of churn. We're going to build a system to catch it.
We are getting our hands dirty today.
We certainly are. We have a specific technical report in front of us titled O3 Report Basic Pipeline. It's essentially a blueprint. And our goal for this deep dive is to walk through the actual construction of a machine learning pipeline, step by step, line by line.
It's a great document because it takes us from raw, messy, real-world data all the way to a functioning random forest model. It's a perfect hello world for predictive analytics.
And just to set the scene, the data set we're using is the classic Telco Customer Churn data set. It originates from IBM, so it has that, corporate pedigree. But for this report, we are looking at the version on the Hugging Face Datasets Hub. Specifically, the repository is Jossen Jostjes Telco Churn.
I like that we're citing the specific repo. It makes it tangible. This is an abstract math. It's code you can pull right now.
Exactly. So let's boot up the terminal. We're going to act like we're sitting side by side at the computer, building this thing from scratch. The report starts with step 1, loading and initial inspection.
Right. So the first thing we do is get the data into our environment. The report uses the datasets library to pull that Jossen Jostjes repo. But, and this is the first interesting choice the author makes, they immediately convert the train split into a pandas data frame.
Pause there for a second. Why the immediate switch? Why not just keep it in the native Hugging Face format?
It's about the right tool for the job. Hugging Face datasets are incredible for storage, for text, for streaming massive amounts of data. But when you have a table, rows, and columns, and you need to clean it, slice it, and analyze it, pandas is still the king. It's the workbench.
Okay, so we convert it to a data frame. Let's call it a DF. We run df.head to take our first peek. What does the expert eye see?
Well, at first glance, it looks like a standard spreadsheet. You see columns for gender, partner, dependence, phone service, the usual stuff.
Looks innocent enough.
It always does. But the report immediately identifies 3 specific red flags. These are things that, if we didn't catch them right now, would cause the model to crash, or, even worse, lie to us later.
I love a good red flag. Let's unpack them. What's number 1?
Insight number 1 is hidden in the total charges column. This represents the total amount a customer has spent. Now, intuitively, what type of data is money?
It's a number. Dollars and cents, it should be a float.
You would think.
Yeah.
But when we ask pandas what type of data it is, it says object.
Object.
And pandas object usually just means string, text. The computer thinks that column is made of words, not numbers.
Wait, why would it think money is text?
Usually it means there are some sneaky, non-numeric characters hiding in there. Maybe a space, maybe a symbol. But the point is, if we feed text into a mathematical algorithm, the pipeline explodes. You can't multiply the word money by 5.
So red flag 1, the money column is disguised as text. We have to fix that. What's number 2?
Categorical overload. This data set has 21 columns. A whopping 17 of them are categorical.
Meaning they're text-based choices, like yes, no.
Exactly. Yes, no. Fiber optic, DSL, month to month. Only 4 columns in the whole data set are actual numbers.
That seems like a problem because, again, machines speak math. They don't know what fiber optic means.
To a computer, fiber optic is just a random string of bytes. It has no value. We are going to have to translate all of those words into numbers. That is going to be the heavy lifting.
And the third insight.
Class imbalance. This is about the target we're trying to predict, the churn column. It turns out we have significantly more customers who stay than customers who leave.
Well, from a business perspective, that's good, right? You want people to stay.
Great for the CEO. A little tricky for the data scientist. The report notes it's not severely imbalanced. It's roughly 73% staying and 26% leaving. But if we ignore it, the model might get lazy.
Lazy how?
Imagine a test where the answer is false, 73% of the time. If you just guessed false on every single question without even reading them, you'd get a 73%.
You'd pass.
You'd pass. The lazy student strategy. The model just guesses everyone stays and fails to spot the people leaving.
Which is the entire point of this pipeline.
Exactly. So we have to prevent that.
Okay, so we've surveyed the land. We know the pitfalls. Let's move to step 2, preprocessing. Time to clean up the mess. The report starts by dropping a column. Customer ID.
This is standard practice, but it's important. Customer ID is, a random string like 7590 VHVEG. It identifies a record, but it has 0 predictive value.
Right. A customer isn't going to cancel just because their ID starts with a V.
Exactly. If you leave it in, the model might try to find a pattern there where none exists. It's just overfitting to noise. So we drop it, get it out of there.
Bye-bye, ID. Now, let's go back to that total charges issue. The money column that thinks it's text, how do we fix it?
The report uses a very specific command here. It's one of the most useful tools in Pandas, PD.2 Numeric, with the parameter errors coerce.
Coerce. That sounds aggressive, like we're bullying the data.
We kind of are. It basically tells the computer, force these values to be numbers. I don't care what they look like, make them numbers.
And what happens if it finds something that can't be a number, like a blank space?
That's what the coerce part does. It says, if you find something unreadable, don't crash, just turn it into NaN.
NaN, not a number.
Right. It's a placeholder for missing data. And this leads to a huge aha moment in the report. Once we forced that conversion, we check which rows turned into NaN.
And what do we find? Why were they unreadable?
They were blank strings, just empty spaces. And the report notes that these blank values likely correspond to new customers people with a tenure of 0 months.
Ah, that makes perfect sense. If I signed up today, I haven't received a bill yet.
Correct. So my total charges effectively doesn't exist. The database just left it blank.
So here's the million-dollar question. How do we fill that hole? Do we just delete those customers?
No, you never want to delete data if you can avoid it. This is where business logic trumps code. The report decides to fill those NaN values with 0 now.
Because if you haven't been billed, your total spend is $0.
Precisely. It's not just a technical patch, it's a reflection of reality. Always let the business context guide the cleaning.
I love that. It's a small detail, but it really separates a coder from a data scientist.
Okay, next up in step 2 is separating the data. The report mentions splitting train data and label.
Simple housekeeping. We just rip the churn column out, that's the answer key, and save it separately as label. Everything else is our train data. It prevents us from accidentally using the answer to predict the answer.
Which brings us to step 3, encoding. We have all those text columns, fiber optic, yes, no. How do we translate them for the machine?
We use a technique called one-hot encoding. In Pandas, the command is pd.getDummies.
Get dummies. I always found that name a little insulting, but I guess it's descriptive. How's it work?
Well, it creates dummy variables. Imagine a column for internet service with 3 options: DSL, fiber, and no internet. The machine can't process that. So getDummies explodes it into 3 new columns: is ICSL, is fiber, and is no internet.
And these new columns are just filled with 1s and 0s.
Exactly. If you have fiber, the is fiber column gets a 1 and the others get a 0. It's a binary language the model understands perfectly. But the report highlights a specific parameter here. Drop first. True. Why are we dropping the first one?
To avoid redundancy, it's called the dummy variable trap. Let's use a simpler example. Imagine a gender column, male or female. If I have a column is male and it has a 0.
Then you already know the person is female. You don't need a separate is female column to tell you that.
Bingo. If you include both, you are feeding the model the exact same information twice. It introduces something called multicollinearity, and it just makes the data set larger than it needs to be. Drop first. True keeps things lean.
Smart. So we've gone from text to numbers efficiently. Now, looking at our data, everything is numeric. We are ready for step 4, the train test split.
Almost. We have one last text string to convert, the label itself. The churn column is still yes and no.
Right. So we just swap them?
Yep. The report maps yes to 1 and no as a 0. It converts it to integers. The report does mention a future warning here.
That sounds scary. Should we worry?
Nah, not really. In a production environment, you'd want to be more explicit about data types to suppress it. But for this pipeline, it's safe to ignore. The logic holds up.
Okay, now the actual split. We are using train test split. The report specifies a test size of 0.2.
Which means we are holding back 20% of the data. Okay. This is our holdout set. Yep. A model never sees this 20% during training. It's the final exam.
And here comes another one of those parameters that feels super important but easy to overlook. Stratify label.
This is absolutely critical. Remember that class imbalance we talked about? Roughly 26% of people churn.
Right.
If we just split the data randomly, we might get unlucky. We could accidentally end up with a test set that has like 0 churns.
Or a test set that is only churners.
Exactly. It would be an unfair test. It's like tasting soup. You don't just skim the broth off the top. You stir it first to make sure your spoonful is representative of the whole pot.
I'm getting hungry.
Stratify label is that stir. It forces the split to respect the original percentages. It ensures that if the original data is 26% churn, the training set is 26% churn, and the test set is 26% churn. It locks it in.
And the report confirms this, right? It prints out the distributions.
It does. It shows roughly 73.5% non-churn and 26.5% churn for both sets. That proves our split is representative. We aren't comparing apples to oranges.
Okay, the data is prepped. It's clean, numeric, split correctly. Step 5, we train the beast. What model are we using?
The report chooses a random forest classifier.
Why that one? Why not something simpler or more complex?
For a basic pipeline like this, random forest is the Swiss Army knife. Remember, we just created a lot of columns with that one-hot encoding. Random forests handle that high dimensionality very well. They're also pretty robust to outliers. It's a great starter model.
And what settings or hyperparameters are we giving it?
3 key ones. First, an estimator's 30. That means we're building a forest of 30 decision trees. It's enough to learn the patterns, but fast enough to run on a laptop. Random state 42. This just ensures reproducibility. If you run the code and I run the code, we get the exact same result.
And the third one? I have a feeling this relates to our imbalance problem.
You guessed it. Class weight balanced. This is the direct solution to insight number 3.
How does it actually work?
Think of it like a penalty system. Since we have fewer churners, the model normally doesn't care as much if it misses one. Setting this to balance tells the algorithm, hey, these churn cases are rare, so they are more valuable. If you get a churn case wrong, I'm going to punish you more.
So it forces the model to pay extra attention to the minority class. It puts a thumb on the scale.
Exactly. It's like giving the model a pair of glasses specifically designed to spot the people who are leaving.
That is such a cool lever to pull. So we run FET, the model trains, and now...
The moment of truth. Step 6, evaluation. How do we do?
Well, the headline number is accuracy. The model gets approximately 78.9% accuracy.
Which sounds okay.
Almost 80%. That sounds pretty solid for a first try. I'd be happy with an 80 on a test.
Hold your horses. Don't pop the champagne just yet.
Uh-oh. I hear a butt coming.
Accuracy is the most deceptive metric, especially with churn. Remember, about 73% of customers don't churn.
Right.
If I wrote a really dumb program that just printed no churn for every single person, how accurate would I be?
You'd be right 73% of the time.
Exactly. So our fancy machine learning model got 79%. That's only 6% better than a dumb guess. It's better, sure, but it's not a slam dunk.
So accuracy is a vanity metric here.
It can be. To really understand performance, we have to look at the confusion matrix. This breaks down our test set, about 1,400 customers, into 4 buckets.
Walk us through the buckets.
First, the good stuff, true negatives, 922. These are the happy customers the model correctly said would stay. Then, true positives, 189. These are the churners the model correctly caught.
Okay, so far so good.
Now, the bad news, false negatives, 185.
Ouch. What does that mean in plain English for the business?
It means there were 185 people who actually left the company, but our model predicted they would stay. We missed them. They just walked out the door, and we didn't even see it coming.
And looking at those numbers, we caught 189, but we missed 185. That's essentially a coin flip.
Correct. And this is reflected in the classification report. If you look at the recall score for class 1, for churn, it's 0.51.
51%. That confirms it. We are only catching half the churners.
The model is pretty precise when it does predict churn. The precision is 0.63. But that recall of 0.51 means it's just not finding enough of them. It's playing it too safe.
So from a business perspective, this model is letting half of the at-risk people slip right through the cracks. That's a lot of lost revenue.
It is. We call this a low recall model. It's conservative. It only raises the alarm if it's really, really sure. But in churn prevention, you usually want to be a little paranoid.
Right. You'd rather send a please stay email to a happy customer, which is maybe slightly annoying, than lose a customer completely.
Exactly. A false positive, annoying a happy customer, costs you a few cents. A false negative, losing a subscriber, costs you hundreds of dollars.
So let's wrap this up. We walked the full path. Started with raw data from Hugging Face, converted everything to numbers, filled the empty billing data with zeros based on business logic.
We encoded the categories, we split the data using stratification to keep the ratios intact, and we trained a random forest using class weights.
And the final verdict.
The pipeline works. As a technical baseline, it is a success. It runs from start to finish without errors and produces a working model.
But the verdict on the model itself.
The code is solid, the strategy is sound, but the result, specifically that recall of 0.51, is the area for improvement. I wouldn't ship this yet. I'd be looking for ways to bump that number up.
So here's a thought for you listening. We used class weight balanced, and that helped, but we still only caught half the churners. The model naturally optimized for overall accuracy.
So here's the provocative question. In a real business context, is accuracy ever the right goal? Or should you deliberately build a worse Model 1 with lower accuracy just to drive that recall up to 80% or 90%?
Is it better to be right most of the time or to be paranoid and catch every potential churner, even if it creates more noise for your marketing team?
Think about tweaking the probability threshold. The model outputs a probability. Maybe we shouldn't wait for it to be 50% sure. Maybe if it's even 30% sure someone will leave, we should act.
Something to mull over before you start your next pipeline. Sometimes the best code isn't the one with the highest score, but the one that saves the most money. That's it for this deep dive.